Welcome to this explainer. Today, we're taking a deep dive right into the central command of modern cloud infrastructure. And I'm going to promise you something right off the bat. By the time we wrap up here today, we are going to completely and fundamentally shift your mental model of how Kubernetes actually operates. You might think you know how your containers get deployed, but the reality is so much more brilliantly orchestrated than it appears on the surface. We're unlocking the true brain of Kubernetes, the API server. Here's our roadmap. We're going to look at the real Kubernetes core, see why kubectl is just a client, and break down the 6 jobs of the API server. Then we'll dive into the event-driven watch mechanism, exactly how pods are built, and finally designing for high availability. Let's get right into it. All right, part 1, the real Kubernetes core. Picture this everyday scenario. You're at your terminal, you type kubectl apply-f nginx.yaml, hit enter, and boom. A few seconds later, your pod is ready to go. It feels completely seamless, right? Almost like magic. You type a command and your resources just appear out of thin air. But let's pause for a second. Who actually built that pod? I mean, who did the real heavy lifting? A lot of folks assume it's kubectl doing the work right from the terminal, or maybe the scheduler organizing it, or the kubelet spinning it up on the node. Well, we're going to bust that beginner myth right now. You see, the beginner's view usually imagines this straight line from your terminal through the API server straight into the cluster's memory database, etcd. But the reality? It is entirely different. The API server is the sole gatekeeper here. Literally, no other component is allowed to touch etcd directly. Not the controller manager, not the scheduler, not the kubelet, no one. They all only talk to the API server. It's the absolute single entry point for the entire cluster. Moving to part 2, kubectl. It's just an API client. We really need to completely dismantle the idea that terminal tools have any internal Kubernetes logic. When you type kubectl get pods, the tool actually has no idea how to fetch a pod on its own. None. It's really just acting as a basic API client. It translates your command into a standard HTTPS JSON request, fires it off to the API server, and just waits for the response. That's it. Your terminal tool is literally just a messenger. Okay, part 3. Let's look at the 6 jobs of the API server. So if the API server is the one doing all the actual thinking, let's look under the hood at its 6 core responsibilities every single time a request comes in. Let's walk through the exact sequence. First up, authentication. Are you who you say you are? Second, authorization. This checks your RBAC permissions. Basically, are you actually allowed to do this? Third is admission, which is super cool, and we'll dive into that in just a second. Fourth is validation. This one is absolutely crucial because it catches schema errors. Like, if you accidentally request -5 replicas, the API server catches it right here and throws an error to keep the cluster perfectly consistent. Fifth is version conversion. Say a client uses an older format like apps/v1 beta 1, the API server automatically translates it to v1 so old clients don't just suddenly break. And finally, step 6. If and only if all previous steps pass, it commits the storage into etcd. Now, I want to jump back to step 3 for a second, the admission controller. You can think of this as the police of Kubernetes. Right before any data is written, the admission controller strictly enforces your company policies. It can flat out reject requests, like blocking any deployment that tries to use a latest image tag, or one asking for root container privileges. But it can also dynamically modify requests. It can automatically inject configurations, like adding an Istio sidecar or mandatory labels right into your deployment without you having to write a single line of extra code. It's a total game changer. Which brings us to part 4, the event-driven watch mechanism. So now that we know how the brain processes requests, how do all these external components actually talk to it without completely overwhelming it? The key here is that components like the scheduler or the kubelet aren't constantly pinging the API, asking, hey, any new pods? Hey, how about now? That kind of nonstop polling would literally crash the system. Instead, Kubernetes relies on a watch mechanism. It's a brilliantly designed event-driven architecture. The components passively watch the API server. The exact moment a relevant state changes, the API server instantly fires off a notification so they can spring into action. Part 5, how pods are actually built. All right, we've got all our pieces on the board. Let's bring this all together and trace the exact journey of a single pod. It's like this incredible, complex ping-pong effect. First, you send a post request, and the API server stores it. Second, the controller manager's watch is triggered. It spots a new deployment and tells the API server, hey, create a replica set. Third, the scheduler's watch notices a pending pod that doesn't have a node assigned yet. It calculates the absolute best node, then pings the API server back to update the pod's assignment. Fourth, the kubelet on that specific node gets its watch notification, pulls the container image, and runs it. And finally, the kubelet sends a status update right back to the API server. It is a highly choreographed sequence. Everyone is constantly reacting to and updating the API server sequentially. Just think about the sheer scale of that operation for a minute. You typed one simple command, but under the hood, the API server is called over 10 times, honestly, often dozens of times, just to shepherd a single solitary pod through its lifecycle. That brain is working non-stop, coordinating every single minor state change. Finally, part 6, designing for high availability. This brings us to the ultimate question for this deep dive. If the API server is doing all of this heavy lifting for every single pod, how on earth do enterprise environments keep it from just collapsing? Because remember, it's the single point of entry. If it goes down, your entire control plane is dead. Well, the solution is incredibly elegant. Because the API servers themselves are completely stateless, meaning they don't hold any memory internally, they push all of that to HCD, you can safely deploy multiple instances of the API server right behind a load balancer. That way you can easily handle massive enterprise-level traffic. And to keep things running completely smoothly, enterprises use a few specific optimizations to take the pressure off that control plane. They'll enable a watch cache, which dramatically cuts down on direct reads to etcd. They also configure API priority and fairness, or APF, to prevent sudden, massive surges in requests from taking down critical system components. And, of course, they are constantly monitoring things like API latency, errors, and queries per second just to make sure the brain stays perfectly healthy. So, to wrap up, we've seen today that the API server is the undisputed, omnipotent brain, the absolute sole entry point of your Kubernetes cluster. It authenticates, validates, polices, and orchestrates everything through that genius watch mechanism, but it holds zero state itself. So this leaves us with a massive cliffhanger. If the API server is just the processor, what exactly is ATCT storing, and how does it guarantee the cluster distributed, perfectly consistent memory across multiple nodes? Well, that is exactly what we'll uncover in our next explainer. Thanks for hanging out and learning with me today. I'll see you next time.